So my suggestion to you is that we do a rewrite. We're going to make it a squared around everything, okay? There are two steps to it. The power drops down in front. The power goes down by 1. The stuff stays there. But then we multiply by the derivative of that stuff. Now, if I just gave you that problem and said do its derivative, it's a chain rule as well. So you have a negative sign of the stuff times the derivative of the stuff. Okay, so if you got an answer of negative square root of 3 over 2, you forgot to take the derivative of the inside stuff one more time. The derivative of that is negative 1. So I would assume if you did it wrong, that's the most common mistake. So if you got D as an answer, I would assume you forgot this piece. Okay. So that you do have to use pi over 3, but what's great is even if you mix up the half and the square root of 3 over 2, it will fix itself. But so that is an example of a double chain. So you have to keep going until the thing either is already differentiated, or if its derivative is 1, or if its derivative is nothing. Like if you get a constant, then you're done. Okay, so that's just a little bit about that super chain. Be careful again. This notation should always be rewritten before you get started. Okay, so that's a hard one, but I wanted you to see that double chain notation because that is something that could possibly happen. So I wanted you to see how that works, okay? Okay, so now we are going to expand upon the chain rule. We're going to use something called implicit differentiation in lesson 2.6. Now, 2.6 is helpful. Let me show you what I mean by implicit versus explicit. If you have y equals x squared plus 2x minus 7, that formula has been explicitly solved for x. You can say it's y equals all the x's stuff, okay? This equation it is really super impossible to get it to say y equals all the x's. That is not implicit. That is an implicit differentiation type problem because we can't explicitly solve it for y anymore. Okay, so this one we can use all the rules we know. This one is going to force us to use implicit differentiation. Okay, so it's just another new technique to take the derivative of something that before we couldn't. So you'll notice all the equations we've been doing so far in this chapter, they all said y equals, y equals, y equals. Well, we need to know how to deal with something like that. And so that's what this section is all about. So if we want to find the derivative of x squared plus y squared equals 25, to solve it for y, we would get that square root and we have to put a plus or minus in front. So that's why this one falls in this category. We might lose things. It might not always work out the way we want. So instead, we're going to use a technique called implicit differentiation. Did we actually talk about the rules somewhere? No. Anyway, okay. Here's what you're going to do. We want to take the derivative in terms of x. So we think of y as stuff. I don't really know what it is. It's stuff, okay? So when we go to do this, it is a result of the chain rule. that the x's we can just deal like normal. So x squared becomes 2x. 25 becomes 0. But let's talk about this term right here. That is some stuff related to x. Don't know what it is. Okay. So if we have stuff stuck in a power, what happens? We drop the power down in front. The power goes down by 1. But what do we always multiply by? For the chain rule, we multiply by the derivative of the stuff. So what we're going to do to counteract the fact that we don't really know what the stuff is every time we come across a y, we get to use all the rules we know, but we always just tack on a y prime. Okay? And this dy dx, remember, was that notation for y prime. So when they say to solve for dy dx, you're really just solving for y prime. So we're going to just isolate this term so that we can get our y prime by itself. We can solve for it. But we'll have derivatives that will actually be two variable derivatives. Before, our derivatives have always been x's. Now we're going to have x's and y's all mixed up. Okay, so watch. We're going to subtract. No, it's just an equation. Don't freak out. We're just going to subtract a 2x from both sides. Divide off the 2y. We get that our derivative is negative x divided by y. We've never had a derivative like that where the x's and y's are all mixed up. That's okay. We know the derivative. Because now in part B, remember what we found every single time to find the equation of a tangent line. First step was to find your derivative. Second step was to plug in to find the slope of your tangent. Third step, y minus y1 equals m times x minus x1. Those three steps are consistent whether it is an explicitly solved y equals x something equation, or if it is an implicit one like this. We know that y prime is negative x over y. If we're using the 0.34, just put the 3 replaces my x, 4 replaces my y. So my slope is just going to be negative 3/4. It's just an equation of x and y now. So we have to use both the x and the y from our point value. And then we do y minus my y equals my slope times x minus my x1, in this case 3. Now I'm not going to rearrange it. Slope-intercept form is sometimes very helpful if you had to graph it, but hopefully you know how to do that. That's nothing surprising. So implicit differentiation comes after the chain rule because they are completely linked. We think this y is somehow related to x. I don't really know what it is, so I just think of it as stuff there, and I tack on a y prime every time. That's the main takeaway as you do these problems, okay? So then let's jump to this example. This graph, this equation, x cubed plus y cubed equals 6xy, gives you this little loop thing right here. It's called the folium of Descartes. Descartes was a mathematician. The Cartesian plane was named after him. So whoever named this particular equation named it for Descartes. Anyway, the first step says to find y prime. Our equation does not read y equals for us to find y prime easily. So we have to use implicit differentiation. And because the x and the y are touching on the right side, I want you to put a dot between them. We are forced, anytime two variables are touching, to use the product rule, okay? So this one has the chain rule tucked into it, and it has the product rule. So every time we take a derivative of a y, we're going to tack on a y prime. So remember, when we do this derivative, we're going to tack on a y prime. When we have to do the product rule and we ask ourselves, what is the derivative of y? Y prime. I don't know, okay? So let's go ahead and do this. So we're going to get 3x squared. X's are fine. You just do the rules that you know. Y cubed is 3y squared. But how is it related to y? What stuff made it a y? I don't know. So I tack on a y prime. Now, the right side is a chain rule. Think of 6x as your initial stuff, y as your other stuff. First and second. 6x is your stuff. Keep the 6 with the x. It makes it easier. So it's first times the derivative of the second plus the second times the derivative of the first. Every time I took a derivative of an x, don't care, just do it. But when you take a derivative of y, tack on a y prime. Now, all the stuff that contains a y prime, let's get to one side. Every term that does not, let's get to the other side. That's always the next step, okay? So we have the terms that contain a y prime, the 3y squared y prime, the 6x y prime goes over and becomes a negative. The 6y, we're going to subtract off 3x squared because we want to move that to the other side. Now this always is the next step. Factor out the y prime. Whatever's left goes in parentheses. You're always going to divide that off. You found y prime. Don't try to simplify it further than that. Y prime is 6y minus 3x squared, all divided by 3y squared minus 6x. That's y prime. Don't try to factor it. Don't try to go further. Don't try to do a darn thing after that point. You're done. That's it. Now, let's move on to part B. It says, part B says to find the tangent at 3, 3. Now, it doesn't say really what to do with the tangent, so I'm assuming they want tangent line. So let's do that, okay? So the first step is to find y prime, which is above. Great. Second step is to actually plug in the point 3, 3. So every place we see an x, it's going to be a 3. Every place we see a y, it's going to be a 3. So that's going to be 18 minus 27 over 27 minus 18. It's going to be negative 1, but technically that'd be negative 9 over 9, which is negative 1. So our equation of our tangent line, it's the point 3, 3. Our slope is negative 1. It's just y minus 3 equals negative 1 times x minus 3. And the point 3, 3, let's draw it up here, is this point. Our, if we were to arrange our equation, it would be y minus 3 equals negative x plus 3. We would add a 3 to both sides. It's y equals negative x plus 6. So we start at 6, go down 1 over 1, down 1 over 1. It has a slope of 1. So if you were to put the Folium of Descartes equation in, that x cubed plus y cubed equals 6xy, you'll get that little loop. Our graph should, of the line y equals negative x plus 6, should skim it perfectly at the point 3, 3. This is the point 3, 3. And it should be tangent to it. So it is something that you can check pretty easily in Desmos. You'll just have to put that whole equation in for that Folium of Descartes. Okay. Now, the next part is a little harder. They want to know, when is the tangent line horizontal? A tangent line is horizontal when the slope of the tangent equals 0. So they're really saying, when is the slope of the tangent equals 0? Now, unfortunately, this is our equation. A slope is equal to 0, or a number, a fraction is equal to 0, only when the top is equal to 0, okay? So really, it is where that equation intersects this thing. And I use Desmos. I'm not going to torture you or myself to do that. But it's where does this intersect that? So if you go into Desmos, you put your Folium of Descartes equation, you put that parabola, and it hits it in two locations, 0, 0, and then this x value of 2.52. Okay. So there you go for example 2. We're getting into the meat of calculus more, as you can tell. There's lots of stuff we have to memorize. Make sure that you're practicing as much as you can. Don't wait about practicing. Check your work as you're practicing. Come with me at the questions. You guys haven't been asking me a lot of questions. So if you're stuck on anything from the homework, make sure you're asking me, okay? Okay, so that is a pretty complicated problem, as you can see. Algebraically, we should know how to do all that stuff. That's not anything surprising. But, you know, it is very easy to mess something up on a problem like that. It's a difficult problem, okay? So that's example 2. So now let's look at example 3. So we notice that the x and y's are together and not really solvable. It's stuck in a sign. Here, x's and y's are stuck together. This tells us I need to use implicit differentiation on this problem. On the right side, there is a definite product rule. On the left side, there's a definite chain rule. That x plus y is stuck inside. Okay. So first thing we're going to do is remember, we're going to follow all the rules we know so far, but every time we do a derivative of a y, we tack on a y prime. Okay. So how do we deal with the sign of x plus y? Well, the outside function is sine. The inside function is x plus y. So it's just going to be the cosine of the stuff times, in parentheses, the derivative of the stuff. The derivative of x plus y is 1 plus 1 y prime. I'm just going to write that as y prime. The derivative of y is y prime. Okay. Now let's do the product rule on the right side. It's going to be the first times the derivative of the second plus the second times the derivative of the first. Now a derivative of a y squared is 2y, y prime. Okay. So that's initially the answer, but we have to solve it for y prime. So we have some math to do. Okay. Now what's great on the right side is this term is the only one that contains a y prime. The problem here is this is a product, so we have to distribute first before we can actually move terms around. So let's distribute. Okay, 1 times the cosine of x plus y is just the cosine of x plus y. And then we'll have a plus, and then we'll have another cosine of x plus y times y prime. Now we have our terms separated. I'm going to make it look a little simpler, but not much. Okay, so that is, I just made it a little nicer. There is one thing multiplied by 2, so you're going to distribute. That's why I have 1 term and 2 terms. Okay, so I just kind of cleaned it up slightly, didn't do much, but the terms that contain the y primes are going to go to the left. The terms that do not are going to go to the right. We're always going to do that after we get all the terms ready to go. Okay, so I'm going to leave the cosine of x plus y, y prime, and then I have to subtract this one over. So I'm going to minus off 2y prime, 2y prime cosine of x. Now, this one is where it needs to be, but I need to subtract that one. Okay, so it's negative y squared sine of x minus cosine of x plus y. Okay. Now the next step, always the next step, is to take your y prime and factor it out, lay it out in front here. And then you just rewrite the stuff that was there without a y prime in. So this would be cosine of x plus y minus 2y cosine of x. We're going to divide, and then we're done. So you just divide that parenthesis to the other side. We're done, okay? So y prime is, this will be our numerator. This will go under it. So our final answer is negative y squared sine of x minus cosine of x plus y divided by cosine of x plus y minus 2y cosine of x. Now these are not factors. Don't try to cancel them out. If they're added or subtracted, there's no way for us to cross out anything. That is our answer. We're done. Leave it alone. You can't do a darn thing. The only thing that probably they might have you do, like the last problem, is they sometimes might say, what is the slope at the point, you know, pi over 2, 7, or I don't know, whatever it is, okay? So that is how you find y prime. So think about all the things we had to use. We had to use the chain rule. We had to use the product rule. We had to do that. We had to identify where the y primes were, get the y primes to one side, nothing y primes to the other, and then do some algebra, okay? So that pattern is going to happen a lot for these problems. So hopefully you were able to follow what we did for that one, because then that will help you for ones that are like in your homework and stuff, okay? Okay, let's look at this one. Now, do you see how it says a y double prime? That means we have to find y prime and then do it again, okay? So first, okay, let me rewrite the problem. At least the x's and y's aren't touching. The only reason this problem has an issue is because the y to the fourth is an even power, and that messes things up. Okay, so anyway, let's go. So our derivative is 4x cubed plus 4y cubed y prime equals 0. Okay. Now, get the y prime term on one side, the other non-y term on the other. Divide by whatever isn't y prime, and we get that's negative x cubed over y cubed. Okay, so that's our first step. So you can't find y double prime if you don't have y prime. So now we have y prime. So now we're just going to take the derivative of this using our the fact that we're going to have some y primes in there. I'm going to show you what we have to do. Okay, so we're just going to pretend like that's going to be what we use for our y double prime. So we're going to do it again. We're going to do it using the quotient rule, which is the bottom times the derivative of the top. X's just act like they've always acted. Minus the top times the derivative of the bottom, but it has a y in it, so tack on a y prime, all over the bottom squared. Okay, so let's talk about what I did again. Bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. Okay, so I just did the quotient rule. Okay, here's the problem with that. The second derivative should not contain any primes in it. It needs just x's and y's. But what did we find that y prime was? X cubed over y cubed. So we can just take that negative x cubed over y cubed and plop it in there. So let's do that. So I'm going to kind of clean up each term as I go. So this would be negative 3x squared y cubed plus 3x cubed y squared x cubed over y cubed, negative x cubed over y cubed, I'm sorry, over y to the 6th. So I just plopped it in. I know what it's equal to. Plop it in. Okay. Now let's simplify that back term so then I can show you how to simplify the whole darn thing. Okay. So we get negative 3x squared y cubed minus 3x to the 6th over y to the 1st, all over y to the 6th. Okay, so watch what I did. This term, it's good. This term I made into this. Why? Well, a positive times a negative is a negative. 3 is our only numerical constant, coefficient, whatever you want to call it. X cubed times x cubed is x to the 6th. I have a y squared divided by a y cubed, so it leaves me a y in the bottom. Or you could make that y to the negative 1. That's okay too. Okay. Now, the only thing we have to fix is we shouldn't have a fraction within a fraction. That's an easy fix. Just multiply by that inner denominator. The only denominator I have is a y, multiply top and bottom by y, and we're going to fix the problem in one step. So our final answer should look like this. Negative 3x squared y to the 4th minus 3x to the 6th, because those y's canceled out there, over y to the 7th. So that is how we use implicit differentiation twice. It's fun, isn't it? So that is example 4. Okay. So now you got to practice. And please, tomorrow in class and tonight, work on your homework and come back to me. I don't understand how they got this answer. Show me. Come back with good questions, and we can do some together tomorrow. That's what tomorrow is. It's homework day. So let's do it. There we go.